Excellent. I think it's time to start. Can everybody hear me? Yeah, I assume so. Yeah, I get a great thumbs up from Gary. Thanks, Gary. Hey, welcome everyone. Welcome to the launch of the Sequana Webinar Series. For those who don't know me, there will be still a fair few. I'm Frank Fissler, the CEO of Sequana Partners, and I want to thank you all for joining us today here. Before we kick off, I would like to acknowledge the traditional owners and custodians of the lands we are all joining from today and pay my respect to elders past and present. And of course, also offer my respect to any Indigenous people who are joining us online today. As part of the AWA's National Water Week, we are excited to bring to life the theme Accelerating Action with our first webinar on the topic desalination, demystifying its carbon footprint. We are involved in a myriad of desalination projects around Australia at the moment, from smaller scale, but also to probably involved in all the largest ones in Australia that are underway in planning, etc. Here today we have some key people that we worked across many years on the Victorian Desalination Project, and I obviously welcome Julien here in particular, who we work with on the Victorian Desalination Project for many years. This session today is a fantastic opportunity to discuss how Australia can shift the need for reliable, sustainable water source for all through desalination. And I will now hand over to Ian Filby, our National Partner, Energy Decarbonisation and Major Project Delivery at Sequana, our facilitator for today's session. Thank you so much.
Thanks, Frank. I'd just like to start by acknowledging the traditional owners of the lands upon which we meet throughout Australia. We're obviously spread right across this wide nation of ours, and Sequana certainly acknowledges the traditional owners' deep connection to the land and waters that we have the great privilege of living and working on. So we'd like to extend our acknowledgement to those traditional owners. Today's agenda, it's a bit of a journey, journey of discovery, a conversation around desalination, demystifying the carbon footprint. That's the story we'd like to talk to you about. We'll cover some topics that relate to Australia's need for water and how desalination fits into that. We'll give people a bit of a refresher on what desalination is all about, what its environmental impacts might be and can be, how we can minimise those. We'll focus on some of the tricky problems around minimising impacts, thinking about carbon footprint, and then we'll bring some case studies forward for you to think about how we can improve and deliver benchmark desalination projects of the future. Just a reminder to everyone, this session's being recorded, so appreciate at the end. Please feel free to post some questions in the chat function. We'll try to cover as many as we can when we get to the end. Thank you. Our speakers today, I'd like to introduce Gary Crisp, Sequana's Chief Engineer. Gary's got an unrivaled depth of experience in the desalination field, almost half a century of working in this space. He has an enormous number of insights, both technical and anecdotal, and I'm sure he'll share some of those with us today. We've also got Julien Tauvry from Watersure and Suez. Julien is the operations director down at the Wonthaggi desalination plant. He has an enormous amount of experience both internationally in the desalination field and specifically here at our plant here in Victoria. So welcome, Julien, and thank you for joining us. I'm Ian Filby. I'm the National Partner of Energy, Decarbonisation and Major Projects at Sequana. I've worked in the water industry most of my career, but also dabbled in both the earth resources and the energy sectors. So I'm really looking forward to the conversation today to see how all these things fit together as part of our water future. So I just wanted to give you a bit of a snapshot of how desalination fits into Australia's water future. I'm sure many of you already know this, but it's good to sort of pause and reflect on how it fits strategically. If we look across a whole range of drivers, we see that we're faced with challenges that relate to water scarcity, population growth and urbanisation, droughts, climate change. We're a land of limited freshwater resources, and yet we have enormous agricultural and industrial potential. The challenge that we're faced today that makes this even greater is the challenge of decarbonisation. And to answer all of these things, we're seeing globally that desalination is vital. It's a vital part of the global water challenge, and it can provide a stable supply of drinking water for agriculture and industry. So let's have a bit of a look at that in an Australian context. I'd just like to point out a study that was released last year by a study that was called Net Zero Australia. It was a project that was led by the University of Queensland, University of Melbourne, in partnership with Princeton and NAUS Group. It is a very groundbreaking piece of analysis that looks at how the Australian economy and the Australian landscape can face the decarbonisation challenge. I'd encourage you to look up the report if you've got some time later. But within that report, there's a really important insight in regards to the water future. You can see the two graphs that I've selected from this slide, which illustrate a number of scenarios where renewable energy and decarbonisation occurs across the entire economy and the entire Australian landscape. And what you see is an increase, a doubling of the water consumption requirements across our nation. And yet in the same frame of reference, we're seeing a halving of the fresh water consumption taken from the environment. The only way these two things can exist or can occur is if we have a significant increase in manufactured water to supply these needs. And desalination is a really important part of that story. So what are some examples of this challenge and how people across our nation are rising to the challenge? Up in Queensland, we can see the Sequana Water Security Investment Program, which Sequana is involved in, an integrated program of infrastructure planning to meet urban needs. So led by the government, a strategy to meet those needs through desalination, through water treatment plant upgrades. If we turn our minds to another state over in South Australia, we see a state-led initiative to focus on decarbonisation opportunities. The State Prosperity Project in South Australia is looking to utilise critical minerals and green hydrogen at the top of the Spencer Gulf. However, there is a need for water, and the state government has proposed a desalination project in South Australia called the Northern Water Project, which is an example of how a state can lead the way in the decarbonisation challenge. And similarly, over in Western Australia, up in the Pilbara, we see a private sector-led initiative in the Legacy Project, looking to provide desalinated water for industrial users and for local communities in partnership with the traditional owners. And Sequana is very proud to be part of that initiative as well. So right across the country, you can see that desalination is really coming to the fore again to meet our emerging needs. At this point, I'd like to pass the baton over to Julien to give us a bit of an insight as to how the desalination journey is progressing globally and some of the fundamentals that underpin it. Julien.
Thank you, Ian. Just before presenting some of the global trends, just a quick overview of what is desalination when we talk about this desalination process. And so to put it simply, it's really about removing the salt from and other impurities from a certain source of water, be it seawater or brackish water, and to turn it into a specific type of water, mostly fresh water for drinking purpose, but not only. And so this pretty much summarizes what are the different inputs and outputs of this process and what item we're going to focus on more specifically when we are looking at reducing the overall footprint of this process. Globally, we have two big families of process. The thermal category, which is the historical one, started many years ago, if not a few hundred years ago, which is the idea of using heat to produce steam and then condense this steam into fresh water. The two most frequent technologies used currently are the multi-stage flash distillation and the multi-effect distillation. And then next to this, you have the other family of process, which is the membrane distillation, desalination. So most famous through the reverse osmosis process, but not only that, electrodialysis and something a bit more emerging, such as forward osmosis is there as well. If we move to the next slide, you will be able to see how this technology have evolved over the last 30 years. So different important takeout of these two charts. First of all, RO is definitely and obviously the biggest chunk, I would say, of installed capacity in the world. And this has led to a lot of maturity and improvement in the technology. As you can see, the other technologies such as thermal technology are not really increasing as much now. They're slightly improving, but nowhere near what happened with the reverse osmosis. So when we will talk today about desalination, we will mostly talk about reverse osmosis. The other interesting aspect is what you can see on the right of the slide, the other chart, which is where is the desalination capacity installed in the world. So there's no surprise here. Middle East and North Africa is a big part of it. But not only that, and you can see over the last 10 to 20 years, the amount of capacity installed in Asia Pacific has increased significantly. And what it means two things. The good bit, I would say, is that we have access to much more supplier expertise, etc., in this part of the world. The challenge, the flip side, is that with the second wave of desalination coming into Australia, there's going to be a lot of competition for resources and expertise. And in parallel to this, and Hansi mentioned some of them, you have emerging technology that are yet to be fully expanded to large scale, and some of them may never end up in large scale because of the complexity of the technology. But there's some interesting field of research around the type of membrane and even looking at magnetic desalination or hybrid system with solar input. If we can move to the next slide, please. I will focus pretty much on the investment that is forecasted between now and 2028. It's a bit difficult to assess the amount of investment that is forecasted. I'm using here the Global Water Intelligence data, but as we know, it really depends on what's the remit, I would say, of the data we're looking at. What is important to understand is that between now and let's say the next 4, 5, and even beyond that, they're going to be a significant additional investment in capex, and that's why I mentioned before the second wave of desal for Australia, if we were to compare to what happened in the 2010 area. So that's an important aspect, and the ability of the different states of Australia to fund this investment will be important. The other one, which is on the right side, you can see where we stand as Australia compared to other big spending country moving forward. Even the $2 billion can be argued. We think it's much more than that, but just for the sake of comparison, it's interesting to see where we sit compare other countries, either Middle East of Asia Pacific. That clearly shows that the planning part will be very important to ensure that Australia is in the best possible position to invest and deliver this second wave of desalination. So that's it for this part. I think now I'm going to hand over to Gary to talk about some environmental aspect of desalination.
Oh, hi, everyone. Yeah, obviously, I'll talk about Perth Seawater Desalination Plant again, but it's very important because this was the first plant, and we had to get past the public from both the energy point of view and also the discharges and intakes can be very controversial. So 2 years after the plant was operating, two people that worked for the operator and for the Water Corporation, Steve Christie and Veronica Bonnelet, did a paper after a lot of analysis, and it was called the Perth Australia 2-year impact on the operation and environmental impact of Perth desal plant. And after all the assessments, they proved beyond any doubt that they had hardly affected or had not even affected the Coburn Sound, which in fact is a very unique system because it's very enclosed It does not have much massive currents or wind movement. In fact, at certain times of the year, the dissolved oxygen levels fall below those that have been registered as the minimum by the EPA, and the plant actually closes down for a week. So it's important to understand that it's a very tight situation there, and the fact that they're already planning a second plant to discharge into Coburn Sound means that they've had negligible impact on the actual sound and the water quality. So I think it's well proven, and all the other plants around Australia have conducted similar tests, be it Gold Coast, be it Sydney, be it Victorian Desal plant, or be it Adelaide Desal plant, and the second Perth plant. In Western Australia, they have to apply every year with a report to the EPA to prove that there's no deleterious effects. So pretty valid that desal plants aren't damaging the ocean. Thanks. Next slide, please. This slide is going to be just a video we prepared. I just want to add, when I showed this video in California, who pretty anti-seawater desal, one of the guests at the big workshop they had there told me that I should go to hell. I don't think he liked the idea that we can prove that we haven't damaged the ocean. Next slide, please.
Thanks, Gary. That's a great story about how the marine environment can be protected if we do our homework and develop our desalination plants correctly. Another really important part of the desalination story is energy consumption. So we want to dive into that in a bit more detail and just give everyone a bit of an insight as to, well, how much energy you need to make desalinated water and how does it compare to other options. So on the left-hand side of this slide, you'll see some stats that come from WASA. They basically illustrate the energy intensity of producing different kinds of water. You'll see at the top of the table, we've got SWRO, which is seawater, reverse osmosis desalinated water. It typically requires between 3 and 8 kilowatt hours per cubic meter. And that compares to things like conventional water sources, which can be as low as 0.2 or to 1 if you're just using a traditional surface water source with treatment. But what's interesting is if you're trying to move your water resources around across long distances, particularly in a country like Australia, you can see that your energy intensity can equally approach the intensity of desal water, particularly if you're going over sort of 400 kilometres distance. One of the things that we thought would be useful is also to compare how much energy we use in our homes and relate that to the energy intensity of the water that could be supplied from a desalination plant. So we've got a table on the right that just illustrates some basic stats. They're averages across Australia, so please don't take them as specific to any particular region, but they are sourced from reputable Australian sources. So typically across Australia, an average household might use 5,500 kilowatt hours per annum. They might use 180 kilolitres per annum in terms of averages. If all of that water that's supplied to the home came from a desalinated source, perhaps that would have an energy intensity of 3.4 kilowatt hours per kilolitre. That would mean they'd need about 600 kilowatt hours of energy to supply that desalinated water. If you compare that to their annual energy use, it's about 11%. It's about the same as what they might, the energy they might use in all their electronic and electrical equipment in their home. So while desalinated water is energy intensive, it is important to keep it in perspective to the other energy uses that we as everyday users consume in our homes. So what does that mean, though, in terms of how desalination plants are developed? The next slide, please. Energy does not equal carbon. It did in the past, but when we look to the future, everyone is working on the basis and is working towards a decarbonised future using renewable energy. And we know that because we see proponents taking it very seriously. Proponents of desalination projects are looking to demonstrate their credentials through initiatives like the Infrastructure Sustainability Council certification scheme. And while a 50 gigalitre desalination plant might require, for example, 40,000 tonnes of CO2 equivalent during construction and up to 170,000 tonnes of CO2 equivalent if unabated using today's energy sources, almost every plant around Australia is looking to abate and mitigate that energy or that carbon footprint. And it's really important because when we look in the wider domain, there are many studies that misrepresent the carbon footprint of desalination plants in Australia. We see that they do not acknowledge that electricity supplied to most plants are from renewable sources, and plants also have offsets. Grid connected doesn't necessarily mean grid intensity. We're seeing some projects in remote areas where off-grid solar-powered desalination plants can achieve carbon footprints that are as low as 0.2 CO2 equivalent per cubic metre. So that's essentially the same as a traditional water source. And we're really pleased to see that the Alkimos plant over in Perth, in its EPA approval, there are commitments in there to achieve net zero. How are they doing that? They're doing that through renewable energy, through the purchase of large-scale generation certificates and emission offsets through ACCUs, through the Australian federal government. So you can see there is a way forward to decarbonise our desalination plants, but there's a lot of work to do to get it right. So I'm going to pass back to Julien to tell us a bit more about how we can do it.
Thank you, Ian. So, yes, first of all, when we try to reduce the energy, we need to understand where is the energy consumed in the desalination process. So it is a bit hard to summarize because each and every project has its own specificity, and the specificity is reflected in the breakdown of energy consumption. So what I'm going to give you here, it's indicative numbers, but that give you a good idea as to where should the attention be focused on to, I would say, deliver the best result as possible from energy savings point of view. So as you can see on this donut, reverse osmosis, the process at the heart of the desalination process, will consume anywhere between 50 to 90%, once again, depending on the type of water you use, depending on the location of the plant, etc. The idea is that it is really where most of the attention is focused to reduce the energy. And as I mentioned previously in another slide, the fact that the reverse osmosis technology is quite mature means we've already achieved significant savings in terms of energy consumption. We are now in the phase of optimization, okay, when we look at the type of technology we use. But what is important to think about, it is not just the reverse osmosis. You have other elements of the process that will consume a certain amount of water. And Ian was also mentioning the transfer. The transfer is a very important element of any water supply project. And this is where finding the right balance between being as close as possible to the customer will reduce the energy spent on energy for transfer, but you may find yourself too far from a source of water that you can use, seawater or brackish water. So therefore, this idea of looking into the overall design will drive, in fine, the bigger picture from an energy consumption point of view. So if we move to the next slide, I will just give you some example as to what can be done to reduce overall the consumption of a project or to reduce the footprint of a project. And as mentioned by Ian previously, it is not necessarily the same thing, okay? But most of the items I've shown on this slide are related to energy. So what we're trying to do here, and I already mentioned where you're going to locate your plant, but there's other element. What's important to understand is that what's your starting point, what's seawater you're using, and what's your target, what's your drinking water target, because the bigger the gap is, the more energy you're going to have to spend to fill this gap between your starting point and the end. So you need to find a reasonable, I would say, balance between your starting point, trying to find the best water as possible, and your target water, making sure that the water quality target are reasonable and serve a bigger purpose. Then after, you will look at also understanding how you can maximize the effectiveness of your pretreatment. Why is the pretreatment on the reverse osmosis very important? Because if it's operating well, it will extend the life of your membrane. It will put this membrane in the best possible scenario for operation. So by putting extra effort on the pretreatment aspect, you will maximize the effectiveness of your membrane and therefore reduce your overall energy consumption, and also reduce the whole of life cycle cost, because you will extend the design life of this asset. Therefore, you will have to replace them less often, and you will create less residue for landfill, for instance. So that's another important element. Another one I wanted to highlight is when we think about energy efficiency, we need to think about the entire process line, not just the final electrical consumer, and we were talking about the membrane or pump. There's a lot of other elements upstream that we need to think of and focus on. That will be the electrical motor, that will be the cable, the connection, that will be the variable speed drive, that will be the transformers. So it's very important to follow the entire process line from an electrical or electricity consumption point of view, because we will find some interesting trends and interesting improvement in this field. Other element will be more about how you managing your operation, generally speaking, how you select your consumable, what you can do to extend the life of your consumable, what you can do to reduce the amount of residue that you are creating, such as sludge from pretreatment. So there's no one answer. It's a sum of a multitude of little optimization that will lead to a reduced profile of the plant. And then we can move to the next slide, which is, if we look at a higher level, and Ian already touched on this topic a little bit, the way we source the energy is important. And there's an important trend worldwide and in Australia in particular with the increase of renewable energy. But we also need to understand that for desalination, and reverse osmosis in particular, a guarantee of securing a base load is very important. So this is why the mix of renewable energy and how we can ensure this consistent base load is important. And so the different way of achieving this reduction of carbon footprint, it can be by offset, such as the power purchase agreement. Example is the REX scheme that is available. You can also integrate the production of energy with another production of renewable energy. So at the supplier level, they will then do this mix to ensure that overall the energy is offsetted. Then after, on the site level, you can also either generate your own energy or try to find within your process opportunities to recover some of the unused energy or unused sources of energy. Solar and wind is an example to complement what we already consuming. Using the brine as well, brine not only as a physical stream, i.e. as with a pressure and with a flow, we can also, and it's an important trend at the moment, we can also look for extracting or the valorization of the brine. What can we extract from the brine that will help to reduce the overall footprint of the plant? A typical example, which is quite interesting, is that there's some research at the moment to extract CO2 from the brine and see where this CO2 can be used as part of the post-mineralization process. So, for example, Suez is working on that concept. You can also look at mining some specific minerals, such as magnesium, from the brine, etc. So it's not just about, I would say, the energy. It is also the circular economy within the process. And then finally, what I would like to highlight is that AI is a very big is a buzzword that you probably hear once or twice every day. In the context of operation and maintenance of a desalination plant, the idea behind AI and machine learning is to be able to really process this huge amount of data that is generated every day, every minute, every second on the plant, and to use this data to help the operator to optimize the process line and to optimize the maintenance with predictive maintenance, once again, to maximize or to reduce the life cycle cost of the asset in particular, but of the whole plant in general. So these are examples of strategies that can be put in place either to reduce the energy per se, consumption, or to reduce the overall carbon footprint of the process. And I will now hand over to Gary for the next slide.
Once again, everyone, I'll re-quote my 20-year-old quote, seeing that's topic of conversation right now. It's not about water, it's about energy. So I've always said in semi-arid countries, if you've got clean energy, seawater desalination is probably the most environmentally friendly source of water. I'm not talking about Canada where they've got tons of water. I'm talking about Australia and semi-arid countries. But to get back to energy, we're talking about carbon footprint minimization here. So a big issue around the world, and at the moment, you saw how many desal plants are coming to the world and already been built. There's something like 14 million membranes going to waste every year. So the whole idea for this whole cycle is to try and to minimize the amount of waste that goes to landfill. And there's many ways of doing it. There's, as you can see in this inverted triangle, there's some ways you can try and extend the life. And I have to say there's plants in Australia that have got membranes that are well over 15 years old through good pre-treatment and management. You can reuse them elsewhere for the same purpose, but for a lesser quality water, and that's reused. You can repurpose them. You can convert them into, say, nanofiltration membranes or use them for other kinds of treatment. The topic I'm going to get onto is recycling, but I'll just go through the last two as well. You can also have energy recovery, which is putting them in incinerators for waste to energy plants because they've got a high calorific value. And then lastly, which you don't want, is land disposal. But from the recycling point of view, there's been lots of ideas. There's been devices made that can take them apart so that you can select different components and get those different materials back into other manufactured components. But the one thing that you could do is if you shred them, and we are working along with the Water Corporation, Fulton Hogan and Curtin University with an idea of using them in asphalt, shredded membranes in asphalt. They are hydrocarbon based, and we figured they would blend well with asphalt and form a nice reinforcing kind of fiber layer. They do that with tires already. In fact, I'm in Bustleton today, and I know there's roads around here that have been done with truck tires. As a component of asphalt. So right now, Fulton Hogan and Curtin University are busy trialing this, and we believe it's going to be a solution or part of the solution to dispose of old membranes. And we're actually presenting this along with the Water Corporation at the IDRA, International Desalination and Reuse Association conference in Abu Dhabi in December. So that's one way forward. Next slide, please. So now we'll do some case studies and success stories. Next slide, please. Just before I start here, I'm not promoting any specific companies. I just thought I'd use these companies which I've shown here because they have been doing have some developments in membranes and membrane spaces. So the first is the DuPont membrane, where they've can actually supply them as dry elements. This has many benefits. First of all, When you transport them, they're lighter. They're not containing sodium bisulfite as a preservative. You don't have to wash them and clean them beforehand. Sorry, and also you don't have to store them in special under special conditions. So that's one way of reducing carbon emissions by providing them dry, that they don't need extra attention. And then there's algae that's produced membranes with bigger spaces. So this gives you a lot of benefit in footprint, reduces your footprint because you can put the efficiency is much lower because the membrane area is much increased. So that's one other aspect in reducing footprint size and also making membranes more efficient. Next slide, please. And then there's a lot of developments going on in the United States. One of them is Aqua. They've got their new 3D printed membrane spaces. So the membrane space is very important with membranes because we can't overcome thermodynamic principles. So you've got your osmotic pressure, which is there, whether you like it or not. You can't change physics. However, you can make the efficiency of the membrane better by reducing friction. And what these new membrane spaces do is they minimize the friction of the water flowing between the membranes, be it the feed spacer or the product spacer. And because they 3D print them, they can be more accurate, they can design them better, so there's less energy loss there. Once again, it's all about energy. So, and then the other is by the University of Connecticut. They've developed a way of spraying membranes to any dimension they want to more accurately than the conventional way of making membranes. This results in smoother membranes, once again reducing friction, and thinner membranes, allowing more membranes per membrane capsule. So that's another way of minimizing footprint and reducing energy consumption. So a lot has been done in the membrane space, excuse the pun, but we'll see what happens with the competition that goes on. But ultimately, the energy consumption of desal plants is almost at its limit of efficiency at the moment. There's not going to be a major jump in steps in reducing energy from what we have now, but it'll still move forward slowly, as Julien mentioned, with AI and machine learning, and obviously the membrane companies competing to get even more efficient membranes. Next slide, please. And then something we've been thinking of in the West, in Western Australia and Australia in particular, we're very concerned about disinfection byproducts because a lot of the water, in the case of Kwinana desal plant, they blend that water with groundwater from the Yarragadee aquifer, and there is a natural amount of bromide in seawater, and so Water Corporation has very strict limits on bromide down to 0.1 milligram per litre, even though it's much lower than Australian drinking water guideline principles. The reason for this is they're concerned about the formation of THMs and disinfection byproducts when they blend the water. So the fact that they're so strict on the amount of bromide in the product water down to 0.1 milligram per litre, they have an extra amount of second pass desal. And we were thinking that one way of trying to reduce or remove the second pass in total, which is capital and energy intensive, is to replace that with a bromide removing resin, so that you can either minimize the second pass or make it much smaller. So it's something that's been looked at. They do that for boron. There's a plant in Cyprus where they've removed the second pass. They're very strict on boron because of citrus. So in the case of Cyprus, they've removed the second pass and put in a boron removal resin. So this could be a way forward, and it could minimize energy, and it could also be used for the smaller plants where you don't want the complexity of a second pass. Next slide, please. And then just the last of my case study, I know once again we're trying to minimize energy. So because we've got the energy minimized, it's just about as much as possible as far as the RO process is concerned, you can look at all the other ancillary process to try and minimize their energy. So one way of looking at it is to try and minimize or improve the efficiency of your pre-treatment process. And we've all heard that ceramic membranes are starting to come to the fore, be they flat sheet or monolithic. So in the case of the flat sheet membranes, I know trials are currently underway in Singapore at Suez 3 by removing the DAF system and the polymeric ultrafiltration system in one of the cells and replacing it with ceramic flat sheet membranes. This is much more robust and can remove all those components we see removed there. One of the components that I would love to see taken out of desal plants in the future is the cartridge filters. They end up in landfill. I believe they also incubator for biofouling. So you can almost remove all of those 5 processes and replace with ceramic membranes. We know they're very expensive, but they're also very energy efficient. A lot of them work on vacuum at a very low head and provide very, very good quality water. So that might also extend the life of the RO membrane. So we may be seeing some step change here. I personally believe we're going to see a ceramic invasion into the future. Thank you very much. Next slide, please.
Thanks, Gary and Julien, for that really in-depth and broad overview of the desalination process and the technologies that underpin it, how we as an industry can continue to drive innovation and drive the carbon footprint down for the next wave of desalination plants that are coming our way. Now it's certainly time for some Q&As. So if you would like to pose a question to the panel, please use the Q&A function on your screen over to the right. Please post them there and we'll take some questions. Just wondering if we've got someone. I think it's Mark Trenbarth. Over the past 15 years, state governments have embraced seawater desalination for security. Queensland has an election on Saturday, and with a change in government looking likely, the opposition have recently stated they are against desal in favour of dams. Have we got any comments? Well, I certainly think that we Sequana, as I guess advisors to governments around the country, certainly acknowledge that policy development is something that is for, I guess, the political process. It is important that we as advisors give them the best advice we can. And I think our role, and I think many of the people on this call, need to just keep giving the best advice we can to both our clients and to our partners across industry on what are the options. The best thing that we can provide is a fact base so that the policy debate can be played out in an open and transparent manner. I think that's probably my response to that question. Gary or Julien, would you like to add anything to those?
I have a quick response, and it's basically what I believe is that one should always ensure that there are available sites for desal. So whether you're going to build desal plants or not, whether you're pro-desal or anti-desal, or you think it's a further long-term solution, I believe in securing the sites as soon as possible. And I did find that where I was in the past at Water Corporation, they were very proactive in making sure that future sites are available, because once they're normally in good spots close to the ocean where everyone wants to build beautiful homes, and eventually you cannot find a spot for your desal plant. So whether you build them now or later, always ensure that you've done the homework and the planning for the right selection of the location. That's my point.
Thanks, Gary. Julien, did you want to chip in on that one?
No, I don't have any specific view, other than I think each case have to be looked at on its own merit. I don't believe that there's a one solution fits all. So it's really about understanding each situation, the customer requirements, the nature of what we're trying to achieve. But I think that's the most reasonable way of approaching every issue.
Thank you. Next question was, through AI and robotics, will there be a big shift in any of the processes or the approach that we see for desalination? I'm
happy to talk to this one a little bit.
Yeah.
I wouldn't say a shift or a very low one, because the challenge is that while the technology of data processing is available, our ability to extract this and to make it work on an operation and maintenance level takes time, because you need to integrate all the learning into, I would say, your system, etc. So there will be some improvement, and there are already, but it's not going to be a quick shift. However, if I flip this aside and go to the more the design phase and the product the development aspect, membrane or other element, there may be a bit more impact on that from a procurement point of view. But on the pure operation and maintenance, yes, there will be an impact from AI, but I see it as a gradual process as we progressively integrate the learning from the machine, or more generally speaking, from AI.
Thanks, Julien. Next one's a really great question that goes to how we might have plants operating in the future. Can desalination plants be flexible and I guess flex up and down with the availability of renewable energy like solar and wind? Julien, Gary?
I'm happy to start, and then I will hand over to Gary. While it may be a challenge, nothing is impossible when you think about it at the beginning. When you take this consideration at the very beginning of planning what you want to achieve, etc., there is opportunity. Having said that, the ability of, for example, turning a big desal plant during the day when there's solar and turn it off when there's not enough power available, it's challenging, because of the size. The scale make it a little bit more difficult, but it's not impossible. It is a matter of making sure that this is taken in consideration at the very beginning of the planning, at the very beginning of the concept design, and to think a little bit outside of the box. Okay, using them as a battery is not a crazy idea in some instances, but not all area can do this type of thing. So it's really about thinking it early and trying to think outside of the box to try to see what are the different options available. I don't know Gary, what's your thought on it?
Okay, it's a good question. So the problem is when you make a plant variable is that you put a lot of capital into something that's not producing 100%. So that's the one aspect. You can move them up and down to follow the power. They do that in Israel. IDE have got plants that buy a cheaper power at night, so they operate them when the power's less. So it can be done, but you'll have to do the whole life cycle cost, net present value of the whole system to see whether it's worth spending that extra capital for something that's not going to run at 100%, or put that capital that you would have spent on making the plant bigger so it doesn't run 100% into some renewable source. So it comes down to the economics and also the size of the site available, because if it's not running 100%, you've got a much bigger footprint than what you're producing. So that would be my view.
Thanks, Gary. Next question's a real technical one. Are there any examples of using osmotic pressure between brine and lower salinity water, potentially wastewater, to generate energy?
So I can climb onto that one. Okay, so many years ago, this was the big buzz. Even 20 years ago, a lot of people were working this. A company out of Norway called Statkraft actually built a pilot plant and ran it for a few years. The problem with that is the differential between the brine and the seawater isn't that significant, and the capital investment in that component doesn't warrant the amount of energy you get back. So many years ago, before we even thought of Alkimos, I did a study for the Water Corporation looking at a plant at Alkimos and using the wastewater treatment plant that's adjacent to see how much energy we could get back. And from a 300 megaliter seawater desal plant, you could theoretically glean back 5 megawatts. However, there's a lot of capital involved and a lot of operations involved, and you've got reverse running membranes. So there's all the issues that you have with seawater desal plant, but in reverse. So it's a good concept, but I personally don't believe it's going to happen.
Julien, have you got a view on that one?
No specific view. I don't have enough knowledge on this.
No worries. Thank you. All right. Oh, sorry. Excuse me. Are there any examples of a digital analytics platform introduced on an existing plant for operational efficiency and reliability where they've really shown some positive results?
So there are platforms out there, and as I mentioned before, one of the challenges, there's two challenges. First of all is the integration of this platform onto an existing plant and how you're dealing with existing database, asset database, existing practice, etc. And then how can you assess the benefit out of it? Because when we talk about asset management, you may see some benefit fairly quickly, but most of the benefit will be in the longer term. So it's a bit of a challenge to really, when you want to assess, let's say you have 3 or 4 different platforms in front of you, and to try to change which one will be best suited for your case, may be challenging. What is very important is that the configuration and the customization of this platform to the specific plant is critical. So I'm of the view that the more flexible the system is, or the more integration you have with the system supplier, the more successful the outcome will be. But it's a tough one, and we know that we have to separate I would say the general description of what a platform will bring you with reality, what's on site. And then the last one, I would say, what is important is a change of mindset as well. When you introduce AI or different type of tools, you need to bring your workforce along as well. It's not just a system, it's about people as well. So there's a big piece of work that is done in terms of training and integration of those platforms in the day-to-day operation and maintenance of the plant. So I haven't necessarily answered black or white this question, but because it's a complex one, and those who are involved in this type of thing know that it's not an easy answer. It's a very interesting topic, but it's not an easy answer.
Thanks, Julien. We've got 2 more questions to go, and then we'll bring it to a close. Next one's probably more something for me to have a crack at. It's with more industry seeking net zero emission outcomes, do we envisage challenges in procuring power purchase agreements with 100% renewable guaranteed baseload? Really great question. I think it's a challenge that we're seeing right across our economy, because the impetus and the need to go to 100% renewables is not an easy task. I think what I would say is it'll continue to change. We're seeing both the energy markets evolve. We're seeing completely new ways of buying and selling electricity and power emerging. I guess one of the thoughts I have is that 100% of anything is often very expensive. And if you can buy something that's 95%, it might be a very good outcome. So one of the challenges for us, both as an industry and for our governments, is to find practical and pragmatic ways of moving towards net zero, setting or meeting the milestones as we go. 2035 targets, for example, are not 100% renewable or completely net zero. So I think it's step by step and finding what the best outcome is you've got at the time. But yes, it's certainly a challenge that the capacity of the renewable sector still needs to grow and expand significantly. 2 more questions. There was a mention of generating CO2 from brine. Would that be through harvesting of algae or through capturing the dissolved CO2? That might be something for you, Julien.
Yeah, so the technology I was referring to is actually stripping or capturing the CO2 that is already dissolved. So I'm not talking about an organic or a biological process. Here it's a physical process of extracting the CO2 that is dissolved in the brine, and then you use it. And the idea is to try to use it in the closest loop as possible, i.e. to use the CO2 generated on site to be used on site as part of the post-treatment.
Yeah. Thanks, Julien. All right. I think we'll bring the Q&A session to a close. We'd really like to thank everyone for their attention today and their interest in this webinar. It's been a great opportunity for us to, I guess, give you a bit of an insight and to take your questions on and have a bit of a conversation. So thank you for joining us. We will be sharing the slides with all the attendees tomorrow. So please, if there's something in there that you're particularly of interest to you, please have a look at those, and you can reach out to us. There'll be some contact details on those slides for getting in contact with us. You can approach us directly or through the inquiry email address that we'll post for you. So once again, thank you to everyone. Really appreciate your interest, and look forward to seeing you again, hopefully on a desalination project in your state or territory in the near future. Thank you.
Bye.
Bye now.